This is intended to be a non-technical description of the steps required to perform a statistical analysis of cross-sectional data. Statisticians organize their thinking according to study design, study question, and unit analysis. You're encouraged to do the same. For concreteness, we'll consider study questions that compare two groups. For example, a group of patients before a QI intervention and a different group of patients after that intervention. We'll begin with a continuously scaled outcome variable. For example, waiting time in a clinic, patient satisfaction calculated from a Press-Ganey survey, distress measured using a subscale of PCM, and so forth. We'll denote this outcome variable by Y. How might a continuously scaled outcome variable be visualized? Well, some obvious choices are histograms and box plots, which the box plot is usually more efficient. The lion's share of the information from a histogram is contained in its percentiles. When you don't have the space to give the picture, you can provide mean and the standard deviation, or various percentiles such as the minimum, the 25th percentile, the median, the 75th percentile, and the maximum. Among others, this visualization exercise explores shape, signal, and noise, and is used to help motivate the choice of analysis. Let's look at the story that the following plots are trying to tell. Looks like waiting time is generally between 30 minutes to an hour, but occasionally is as high as 6+ hours. The mean waiting time is inflated by the high outliers and isn't representative of the main body of the data. Most patients are reporting 100% satisfaction, and of the remainder, many report nearly 100% satisfaction. But there's a minority of patients that are highly dissatisfied. Mean satisfaction isn't a good way to measure the signal here. Distress, on the other hand, appears to follow a bell-shaped curve. Statisticians like this. Here, the mean score for distress is 20 and the standard deviation is 5. For bell-shaped data, 95% of observations will fall within 2 standard deviations of the mean. For distress, that would be between 10 and 30. If the data weren't bell-shaped, there'd be a different calculation, and it turns out that at least 75% of patients will fall in this range. The mean of 20 is a good representation of the center of the distribution. The standard deviation quantifies the level of variation between patients. As previously noted, a quantitative summary for waiting time should probably report selected percentiles, whereas distress could be more simply summarized by the mean and standard deviation. For waiting time and satisfaction, categorizing observations into extreme or not, for example, extremely long waiting time or not, would be reasonable. The usual downside for categorizing continuous data is that you lose information. However, here there's a trade-off in that we shift the focus to the most important element of the data. In practice, you usually report data quantitatively in order to save space, saving the pictures for the most important variables in your analysis. What the visualization exercise does is to assure you that the quantitative summary that you choose tells the data story fairly. The default way for comparing the pre and post means is a t-test. The formula has the difference between the observed means in the numerator and the standard deviation between those means in the denominator. The numerator, the difference in group means, is the signal, the denominator is the noise. Essentially, all statistical tests can be understood as signal-to-noise ratios. The t-test generates a point estimate of the signal, a confidence interval for the signal, and a p-value assessing whether the signal is real. The point estimate is the observed differences between the group means. The confidence interval is that difference plus or minus 1.96 times the standard error. The greater the signal-to-noise ratio, the smaller the p-value, and the more we think that the group means differ. T-tests use group means and standard deviations. It only makes sense when those two quantities are fair summaries of the signal and the noise. So a t-test would be reasonable for distress, but not for waiting time or satisfaction. When thinking about noise, it's important to recognize that there are two types. One type refers to the inherent level of variation in the system, and is represented by the standard deviation. Standard deviation is a property of the system that's being measured. That is, how much the thing that's being measured differs from patient to patient. And that doesn't change as the sample size is increased. On the other hand, the standard error quantifies how accurately you've estimated the sample mean. Being based on both the standard deviation and the sample size, the standard error decreases with In practice, you don't only care whether something is statistically significant. You want to look at clinical significance as well. The most direct way to do this is to derive a minimum clinically important difference, in other words, the smallest difference in group means that matters to you, and ask whether all the points in the confidence interval fall on the same side of this MCID. Loosely speaking, the confidence interval is the set of values of the group means that are consistent with the data, and is something that statistical software can generate for you. The more data you have, the tighter your confidence interval will be. Graphically, the smaller studies are the ones with the wider confidence intervals. The statistically significant studies are the ones whose confidence intervals don't overlap with zero. The bottom study might or might not be considered to be definitive. Point estimate is on the right side of the minimum clinically important difference, suggesting that the difference between group means is clinically meaningful. Most but not all of the points in the confidence interval are on the right side of the MCID, so your interpretation would depend on whether you focus on the most or the all. To estimate sample size, work backwards. This usually involves specifying means and standard deviations. One way to proceed is to specify how narrow the confidence interval needs to be. This is a function of the standard deviation of the sample size. Another way to proceed is to determine how large the study must be in order to declare statistical significance, assuming that the QI intervention works. This slide illustrates the logic behind a sample size calculation based on statistical significance. The top curve illustrates the expected distribution of the difference between group means, assuming that these group means are actually the same. This assumption is called the null hypothesis. For ease of drawing, I've assumed the test is one-sided, so the threshold for statistical significance, denoted by C star, is the point at which the differences between the observed group means would be declared to be extreme. The only thing that null hypothesis is used for in the power calculation is to find that cut point, C star. The power calculation assumes that the true group means differ by a certain amount, ideally the minimum clinically important difference. That's why the lower curve is centered around mu2 minus mu1 rather than 0. The power is based on the area of the lower curve that's to the right of C star. Power increases with increasing sample sizes and with increasing effect sizes, that is, with greater and greater differences between the true group means. If the data don't cooperate, as was the case for waiting time and satisfaction, you'll need to perform a different analysis. Discussion of all the analyses you might perform for these variables is a topic for another day. One option I mentioned was to transform each continuous observation into a binary one by asking whether or not it was sufficiently extreme. For example, whether the waiting time was greater than an hour. Doing this would suggest a comparison of the percentage of extreme values for the two groups. This comparison could be performed using a chi-square test. Suppose that the data are cooperative. What else could you do to make the analysis more powerful? Well, you could include more other variables that predict distress, for example, cancer stage, time since initiation of chemotherapy. If the groups to be compared are similar on these other variables, often called covariates, you gain by decreasing the noise in the system. If the groups are different, you also gain by reducing bias. Adding other variables to the model brings you into the realm of multivariable modeling. Adding other predictors of distress produces models that are called different things by different people. Some call them multivariable regression, also analysis of variance, when the predictors are all categorical, simple linear regression, when you have continuous predictors, and analysis of covariance, when you have both continuous and categorical predictors. So you can see the terminology is based on the scale of measurement of the predictor variables, one of the way that statisticians organize their thinking. Here's an illustration of the thinking of how multivariable modeling can account for case mix. Here the primary predictor is group, namely pre- and post-intervention. The outcome is Y. However, patients differ on the average level of X. Values are lower in the pre-period. Moreover, X is important, so the relationship between X and Y is strong. What the multi-predictor model does, in essence, is to fit separate lines for the pre- and post groups. The vertical distance between these lines compares likes with likes and accomplishes the adjustment for case mix. Now suppose we're dealing with a different type of outcome, a binary outcome. For example, for each patient we can assess whether or not a particular care pathway was adequately followed. For concreteness, this pathway might be that every patient that begins outpatient chemotherapy is called within 24 hours to check on their level of nausea. It turns out that essentially every element of the analysis strategy for continuous outcomes has an analog for binary ones. The visualization exercise is much simpler because the information available for each patient is less detailed. Really, all you can do is just to calculate adherence rates. To compare adherence rates in the pre and post periods, your intuition would say that the statistical procedure should flag adherence rates that are very different as statistically significant, and that intuition would be correct. The test turns out to be a chi-square test. It works by comparing the observed differences in adherence rates with what would happen were those adherence rates to be identical. This latter estimate is obtained by pulling the data. The effect measure or signal can be quantified in various ways, all of which use the same chi-square test. Three common ways to use absolute, ratio, and odd scales is illustrated in this slide. The odd scale doesn't seem as intuitive as the others, although it turns out to be the basis for the most common modeling technique for binary outcomes, logistic regression. Confidence intervals work exactly as before. You can treat them as a black box. Any statistical package will report them as a matter of course, and your task is to take the numbers and interpret them. I've copied a previous slide to remind you how the interpretation process works. To perform a sample size calculation, you typically specify the groups that represent the inputs to a statistical analysis. Here are the outcome rates in both groups. Then you specify power and derive sample size, or specify sample size and derive power. Alternatively, you can base the calculation on the desired width of the confidence interval. To account for the impact of other predictors, it turns out that logistic regression is the procedure to use. The rationale for modeling remains the same, and I've copied a previous slide to remind you of that rationale. When the outcome is time to event, for example, time to death, you use the techniques of survival modeling. Here we've graphed a Kaplan-Meier survival curve, compared them with something called a log rank test. Basically, if all the patients are followed until the event occurs, as was the case for clinic waiting time, you can treat time as if it were just another continuously scaled outcomes. On the other hand, if some of the patients are censored, that is, leave the study alive, you need to use specialized techniques for survival analysis. Recognizing that this isn't a course in survival analysis, the purpose of this session is to illustrate the structure of statistical analysis in various contexts. Let's quickly work through the same exercise we just performed for binary outcomes. The visualization exercise is organized around a survival curve, which represents the proportion of patients that remain alive at each follow-up time. Each time a patient dies, the curve drops. When everyone is fallen into death, the survival curve literally is calculated in this direct fashion. When some patients withdraw from the study alive, there's a workaround. Recognizing that the survival curve is one version of the signal, your intuition should tell you that there's a way to attach a confidence interval to a survival curve, and you'd be right. I didn't illustrate the confidence intervals here. Without them, it's easy to see that the survival curve is better in the post period, but isn't clear whether that difference is statistically significant. The two curves are annotated with a reference to a log rank test that performs a statistical comparison between them. The effect measure in a survival analysis is the hazard ratio, which you can think of as the difference in short-term mortality rates between the groups. For example, as stated, the short-term mortality rate in the post-period, 80% that of those in the pre-period. Details of the survival modeling are a topic for another day. For now, what I'd like to emphasize is the similarity in the structure of all these analyses. We concluded our section with an exercise. We considered a QI study of short-term anticoagulation management pre- and post-intervention using different hospitalized patients in each group. We discussed how to visualize the data, what effect measure to use, the statistical test to apply, and how the sample size